Hi guys, this is Mrs. Allison. We're going to look at solving 1 and 2 step equations. Now ideally this is something you've seen multiple times, but it is always nice to refresh your memory. Just remind yourself of the basics. Or maybe you haven't seen it as often and you need this explanation. So let's review a little bit about solving 1 and 2 step equations. But first, we have to define equation. An equation is a mathematical statement consisting of an equal sign, there's the key, consisting of an equal sign between two algebraic expressions. So let's review what we talked about expressions from before. Remember, an expression doesn't have an equal sign, but an equation does. So an expression, you might see something like 2x plus 3. That would be an expression. Now, if I want to make it an equation, I might change it and say 2x plus 3 equals 9. You'll notice a couple things. One, I've got an equal sign. That's the very definition of having an equation, is there's an equal sign in there. But what you'll also notice is that I have two algebraic expressions. I have the expression of 2x plus 3, but I also have the expression of 9. So I have two equivalent expressions. What's nice about that is we can think about these equations kind of like a balancing scale. That equal sign is like the fulcrum, or the point that keeps everything balanced. So if I want the scale to be balanced, what I do to one side, I have to do to the other side. Okay, so I can't move one of these blocks away without it changing the scales, without it tipping the scales. An equal sign basically says, hey, these two sides are equal right now, they're balanced. But as soon as I move something from one side, it changes the balance. So if I'm going to change the balance, what I need to make sure that I do is use inverse operations on both sides. Well, let's talk operations. What was an operation again? We have operations of addition, subtraction, multiplication, division. So what's an inverse operation? Well, an inverse operation is simply an operation that undoes one of the other operations. So for example, the inverse operation to addition is subtraction, and the inverse operation to multiplication is division. Now, throughout Algebra 1, we will start to talk about various inverse operations for more complicated things like square roots or exponents, and what does that look like? But let's start with our equations. When we're going to solve an equation, the key is showing all of your work. Okay, now I'm going to show you several different ways that we can look at an equation. And you don't have to do it the same way I'm doing this, but I think it's helped visually to remind yourself. One of the biggest mistakes people make with equations is not performing an action to both sides of an equation. So let's look at an example. My first equation says m plus 12 equals 10. This is one side of the scale. This is the other side of the scale. And if I want to keep them balanced, what I do to one side, I have to do to the other. Therefore, if you're a visual person and you like to be able to see what's happening very definitively, sometimes I have people that will draw a dotted line to remind themselves of the two sides of the scale. Okay, so what I'm going to do to one side, I need to do to the other. Now, ultimately, my goal is to get the variable by itself. My goal in solving the equation is to figure out what m equals. So, in the way of figuring out what m equals is this plus 12. And if I want to undo a plus 12, my inverse operation to that is minus 12. But I can't just take 12 away from one side. I've got to take it away from both sides. Now that dotted line that I drew helps remind me that what I'm doing to one side, I do to the other. Now on these one-step equations, it may not be needed to write. But as we start to get into more complicated equations, sometimes making sure that what I've done to one side I've done to the other is important. All right, let's do the math. On the left-hand side, I am left with m. That dotted line represents my equals. And on the right-hand side, I'm going to do 10 minus 12, which is negative 2. So this is my answer, m equals negative 2. But one of the best things that you can do in algebra is check your work. So I'm going to check my work on this. To do that, to check our work, we simply take what we got m to be, which is negative 2. And every place there's an m in the original equation, I'm going to put a negative 2 in place. So we have negative 2 plus 12 equals 10. That's me plugging my work in. And now what I'm going to do is just do the operations as they're listed. Negative 2 plus 12 is positive 10. And positive 10 does in fact equal positive 10. So because I got both sides to be equal, meaning they're balanced, I know I got the correct answer. So my answer is m equals negative 2. All right, try example 2, hit pause, come back and check your work. Hopefully when you did this problem, if you need that dividing line to remind yourself of the scales, you put that in, and you see that you have n minus 9, and you know to undo minus 9, we're going to add 9 to both sides. That is the inverse operation. My left-hand side now will be negative 2 plus 9, which is 7. And my right-hand side just leaves me with n. So we get n equals 7. Oh, now wait a minute. I have 7 equals n written down. Are those different statements? Is it different to say n equals 7 than 7 equals n? The answer is no, it's not different. So let's check our work. These are not different because these are symmetric, what we refer to as symmetric. So let's check our work. If we check our work, is negative 2 equal to, let's put our 7 in place, 7 minus 9. Is negative 2 equal to negative 2? And the answer is yes, so I know I've checked my work correctly. All right, I would like you to try example 3. See what you get. Okay, this is a little bit different, I hope you noticed. I hope you noticed that the operation that's happening here, when we say negative 7y in that order, what we're really saying is negative 7 times y. We don't write the times symbol, but negative 7y is assumed to be negative 7 times y. So to undo this, I'm going to divide both sides by negative 7 because the undoing of multiplication is division. The inverse of multiplication is division. Now, I choose to write my divided by 7 as a fraction. I have seen many people do this same problem. Oops, that's a negative 91. And they write divided by negative 7. These two things say the exact same thing. I just have always done my division as a fraction. I think it's easier for me to visualize. It doesn't have to be for you. So now when I do the math, I'm going to get y equals, and negative 91 divided by negative 7 is a positive 13. And I can check my work. I think that's my answer, but let's just check our work. If I take negative 7 and I multiply it by 13, do I get negative 91? Well, negative 7 times 13, maybe I use a calculator, maybe I can do it in my head. I do get negative 91, so it does check out. All right, if it were me, I would probably star this next problem. Why? Because people freak out when they see fractions, and we don't need to freak out about fractions. A fraction that is written like this, with this division sign right here, which looks like a fraction, really just says y divided by 9 equals 4. That's what it says. So now let's think about division. How do we undo division? The inverse operation of division is multiplication. So what I'm going to do is I'm going to multiply both sides by 9. Okay, let's talk about how we multiply fractions, because right now this is what it looks like. 9 times y over 9. When I multiply fractions, I need to remember that 9 as a fraction is 9 over 1. And what I'm going to do is I'm going to multiply my numerator by my numerator, my denominator by my denominator. So we get 9y over 9 equals 4 times 9, which is 36. Now I'm not done because 9y divided by 9, well, 9 divided by 9 is just 1, so I get y equals 36. And I could check my work. If we check my work here, we would get 36 divided by 9 equals 4. So we get 4 equals 4. And it checks out. So y equals 36. All right. Well, how does that change if I want to solve a two-step equation? It really doesn't change much. It just changes my order of operations. Now we know our order of operations start with parentheses, then exponents, multiplication and division left to right, addition and subtraction left to right. But when I'm solving an equation, I need to undo those in reverse order. For most of our problems, the very first thing that we're going to do is remove the constant term. Do you remember what a constant is? Remember, it's the thing that does not have a variable. Once we remove the constant term using inverse operations, we are going to remove the coefficient, again, using inverse operations. So it's going to look a little bit something like this one. 6x plus 8 equals 50. I'm going to draw for myself the balancing scales to remind myself that what I do to one side, I need to do to the other. And then what I'm going to do is I'm going to remove the constant term. In this example, the constant term is 8. And to undo a positive 8, I'm going to subtract 8. That's going to leave me with, on the left-hand side, 6x equals, for that balancing line, 50 minus 8 is 42. Now I'm going to divide both sides by 6 because I need to undo the coefficient, and 6 is the coefficient. And 6 is being multiplied by x, so to undo multiplication is division. That leaves me with x equals 42 divided by 6 is 7. I really think this is where it becomes more important to check your work. We've got a few more steps, and it gets a little bit trickier. So I'm going to check my work. Checking my work here means I'm going to take 7 and I'm going to plug it in place of x in the equation. So the equation was 6x plus 8 equals 50, and I'm going to plug a 7 in. So 6 times 7 is 42, plus 8 equals 50. Is 42 plus 8 50? And the answer is yes, 50 is equal to 50. So I know I've solved it correctly with x equals 7. But it's always good to check. Now, here's what I'm going to tell you. I would like you to pause, try example 6 and 7, but I'm going to tell you to be very cautious on number 6. This is where a lot of people make mistakes. So hit pause, try it, see how you do, and then come back and hear the explanation. Okay, let's look at 6. Again, I'm going to draw my balancing scales. And I know I need to remove the constant, but what's a little bit weird about this one, 7 minus 3y equals 34, is my constant is listed first. Oftentimes, my constant is not listed before the variable, but in this case it is. And notice the sign of this constant. This is a positive 7. So how do I undo a positive 7? Right, I subtract 7 from both sides. Subtracting 7 from both sides, on the right-hand side, 34 minus 7 is 27. But this is where I need you to be very careful. And in fact, if it were me, I would probably put a star by this question just to remind myself of how tricky this can be. And it starts with that negative sign right there. That negative sign, we need to remember to bring down with the 3y when I simplify the left-hand side. So this should say negative 3y equals 27. Put this star here. If you're going to miss something, this tends to be where people make mistakes. So watch for it now. Anytime we have a negative coefficient, that negative needs to stay with its coefficient. So to undo a negative 3y, or to undo a negative 3 from the y, I'm going to need to do division. But when I divide here, I'm going to need to divide by negative 3 to get y equals negative 9. And then I can check my work. So when I check my work here, I just want to make sure I watch my signs. I have 7 minus 3 times what I think y is, and it should equal 34. And I think y is negative 9, so I'm going to substitute negative 9 in. And I get 7 minus 3 times negative 9. What happens when I multiply a negative by a negative? That's right, we get a positive, so we would get 7 plus 27 equals 34. And 7 plus 27 is in fact 34, so both sides are equivalent. So I know my answer is y equals negative 9. All right, if you didn't feel comfortable before, maybe hit pause again and see if you can try 7. All right, let's check back with 7. I'm going to put my undo or my balancing scale line. And the first thing I'm going to undo is this minus 7. So to undo a negative 7, I'm going to add 7 to both sides. So we get x over 2 equals 16. All right, and just like the problem we did on the front where we had to undo division, because remember x over 2 means x divided by 2. So to undo that, I'm going to multiply both sides by 2. On the left-hand side, what happens is my 2's cancel out, leaving me with just x equals, and now I've got x equals 32. Now, if you're not quite sure if you solved this correctly, you're feeling a little bit uncomfortable about that division part, check your work. It's the easiest way that we can do this. So I'm going to check 32 divided by 2 minus 7 equals 9. And I'm going to do the math. 32 divided by 2 is 16. 16 minus 7 is actually 9. So we get the right answer, 9 equals 9. All right, I've got a kind of funky one. It's number 8. So why don't you try number 8 and see if you get stuck anywhere. All right, hopefully what you did is you drew your line down to say, hey, what I do to one side, I'm going to do to the other. If you need that, you don't have to. I'm then going to subtract 22, which is the inverse of adding 22. So subtracting 22 will undo it. And it leaves me with this fraction. 3/5 x equals 6. 3/5 x equals 6. Now, if I want to undo fractions, then what I need to do is to multiply by what we call the reciprocal. I'm going to multiply by the reciprocal. The reciprocal is just the flip of the fraction. So if the fraction I'm given is 3/5, To multiply by the reciprocal means I'm going to multiply by 5 over 3. And you might think that makes our problem look a little bit more complicated, but watch what happens. We know that when I multiply fractions, we multiply straight across. So I'm going to multiply 5 times 3 and 3 times 5. That would leave me with 15x over 15. 15x over 15, well, what happens if I have 15 over 15? It's just 1x. So the whole reason we multiply by the reciprocal is because the result we get is 1. 1x. It solves for my x. Now, I am going to do the same thing with the 6. In order to multiply 6 with 5 over 3, I need to put 6 as a fraction, which is 6 over 1. And then I'm going to multiply straight across. So we end up with 30 over 3. And 30 divided by 3 is 10. Okay? 30 divided by 3 is 10. So to multiply by a reciprocal, to solve a fraction, we multiply by the reciprocal. And multiplying by the reciprocal means we're multiplying by the flip of the fraction to undo it. Now you'll notice I put 2 asterisks, or 3 asterisks rather, by these next problems. That's because they follow a slightly different order. Up above, we said if we want to solve a two-step equation, we remove the constant term and then the coefficient using inverse operations. However, these two problems are set up a little bit different. And the reason they're set up different is because they're set up as an entire fraction. Okay, as an entire fraction, there are parentheses around a numerator. They're not actually parentheses, but there could be. It is understood that when I have a fraction that this represents parentheses. And I know when I have a set of parentheses, I'm going to do that last because that's the last thing I do when I'm solving. I do order of operations backwards. Okay? So to solve this one, the very first thing I'm going to do is undoing this divided by 8. I need to undo this divided by 8. To do that, I'm going to multiply this whole fraction here by 8 and this by 8. I'm actually going to write it down here just so you can see it a little bit clearer. So I've got this x plus 11 over 8 equals negative 3 times 8. And when I multiply these, 8 as a number, as a fraction rather, is 8 over 1. And when I multiply these, the whole reason we multiply them is because when I multiply them, these 8s cancel out. So when they cancel out, we get x plus 11 equals negative 24. And now I'm back to a one-step equation that I can solve. You'll notice that I'm still working, I didn't draw it this time, but I'm still working down the equal sign. I'm still doing what I'm doing to one side, I'm doing to the other side. And I'm going to continue that because I see an x plus an 11, and I need to undo the 11. So the inverse operation of that is subtracting 11. And we get x equals negative 35. Now I think it would be a wise idea to check your work on this one. So I'm going to check my work. I'm going to plug negative 35 plus 11 over 8, and I'm going to hope it's negative 3. Now remember, having a fraction means that I need to do the numerator first and then deal with the denominator. It's like having parentheses. Even though they're not written, it's like it has parentheses. So negative 35 plus 11 gives me negative 24 over 8. And I'm hoping that equals negative 3. And negative 24 divided by 8 is negative 3. So since both sides are equal, I know that my answer is x equals negative 35. All right. Hit pause. Try to see if you can follow those steps, those ideas with example 10, and then come back. Hopefully you had a chance to try example 10. And what I noticed is although it's in a different order, because there are parentheses, even though they're not written, around the top, I need to undo the denominator first. So the first thing that I need to do is multiply both fractions by 9, or in the case of this right-hand side, it would be 9 over 1, because 9 over 1 is 9. I'm going to multiply my left-hand side by 9 also. And if it helps you, I did that because I'm doing the same thing on both sides of the equation. When I multiply 9 times 4, we get 36. And when I multiply the 9 by w plus 8 over 9, the 9's cancel out. And it leaves me with just w plus 8. And now I'm going to subtract 8. And I get w equals 28. Again, you guys, you have a way to check your work. You have a way to know if your answer is correct. So let's check this. Do I have to check every problem? I don't, but some of these are hard, so you may as well check them and make sure they work. So I'm going to plug 28 in. 28 plus 8 is 36. So I have 36 over 9, which is 4. And it shows that both sides are equal, so I do know that 28 equals W. Now I will say, example 9 and example 10 are some of the harder types of solving two-step equations that we have. So make sure that you pay attention to those. Try a couple more. There are some on your homework. And then there are always extra practice problems that I can give you, so just ask. All right, well, so that's the end of the lesson of solving 1 and 2 step. Hopefully it's a good review for you of stuff you should have done last year. So now it is time for you to work on your assignment. Have a great day.